All right, things are getting more exciting. We just finished discussing standardizing our units of measurement, and we use the international system, Système International, which has 7 base units, these fundamental things that are based on universal constants as of the 2019 definition. And the question now is, what happens if I need to measure something that is not time or mass or whatever? Okay? And the answer is we use what are called derived units, and those derived units are just combinations of base units. And to be a little bit more clear, combinations of base units used to measure non-base quantities. Oops. Again, the base units will get us time and mass and things like that. We can combine those things then to get other quantities we need, like velocity or whatever, and we'll look at a bunch of examples. All right, combinations of base units used to describe non-base quantities. And I've kind of made that term up, but I'm not too disappointed in it. If there's something absolutely critical that I can impress upon your brains, it's the idea that units in science are just like variables in math, all right? Units in science behave exactly like variables in math class. All right, so I'm going to put in a quick and simple example, and if you're not a big fan of math and things like that, you can put that example on pause, but a common variable you might use in math class would be x. So in math, you might have x times x, which would give you x squared, right? In science, you might have something like centimeters times centimeters, which would give you centimeters squared, right? Or similarly, you could have something like x squared times x. And when you multiply variables of like term, you add the exponents. So this will give you x to the third, right? And so you could have centimeters squared times centimeters, and that would give you centimeters cubed, all right? And the same is true as you do division. You could have x to the fifth over x to the third, and when you divide variables of like term, you subtract the exponents. 5 minus 3 is 2, it'd be x squared. And if you had centimeters to the fifth over centimeters cubed, you'd end up with centimeters squared. And then the last thing I want to mention is, what about addition and subtraction? Well, if you had x plus x, that would be 2x. And if you had centimeters plus centimeters, that would give you implied 1 there and implied 1 there, just as we did up there. That would be 2 centimeters, right? And if you did not have the same, and I think that's kind of interesting to look at, if you had, and I'm out of room, but if you had x plus y, that would be x plus y. You couldn't add them together. So similarly here, if you had like centimeters plus seconds, that would be centimeters plus seconds, because those don't add up. They're like a different variable would be in math. So hopefully you can tune back in. It was an important side note, but you may get overwhelmed by the math, which is understandable. Let's then take a look at some specific derived units. And I want to talk about that because in the long term, we're going to reverse engineer our units to figure out our equations. So we'll be doing dimensional analysis at some point, which is a way for us to essentially work without equations. We can just do our calculations based on what the units are, all right? And that is a super powerful tool. So what is an example of a non-base quantity we might need to measure? Well, let's say, for instance, area, all right? And you know area is calculated as length times width, right? So for example, up here we did centimeters and centimeters, so we can go ahead and do that. Centimeters times centimeters gives you centimeters squared. So a unit for area might be centimeters squared. And we know that by kind of looking at the equation there. Eventually we'll reverse engineer it and be able to go backwards. But this is a combination of base units. I guess bad example there. Meters was our unit there. We've got meters squared. So area would be one example. And one step up from area, maybe we want to talk about volume. And volume, you may recall, is often length times width times height. Well, the unit for length is the meter. The unit for width would be the same, that is the meter. And the unit for height would also be the meter. Those are all lengths, and you get meters cubed. And so our unit here would be meters cubed. Now, what other things might we want to mention? Well, what about something like velocity? And I'll just do speed. Speed you calculate as distance over time. So none of the individual base units is going to be good enough, but we do know the base unit for distance or length is meters. And we do know that the SI unit for time is seconds. So we end up with a unit of meters per second. And I do want us to look at this and say later on we can look at meters per second and know that's a speed. So it's important that we can look at these in reverse. What other things might we want? Well, if we up the ante a little bit, we can talk about acceleration. And acceleration is some change in speed or change in velocity over some change in time. And you've seen this triangle, this delta change in. Don't worry about it though for right now, because we know speed is going to be measured in meters per second, and then time is going to be measured in seconds. So you actually end up with meters per second, which is meters per second squared. If we look at Newton's second law of physics, we know that F equals ma. So force. And maybe some of you already know the unit of force is the Newton, but what is the Newton? The Newton's a derived unit based on some of these things that we've already seen. So F equals ma. Well, m is a mass, and that's got to be in kilograms, and a is acceleration, which is, we just figured out, meters per second squared. So it turns out force is measured in kilograms, meters per second squared, which we call a Newton. All right? You've probably seen that somewhere, Newtons before. And just so we're clear here, none of this is something that you need to memorize or do. All I'm doing right here is saying, hey, here are some things we might measure, and here's what these derived units are going to be, and they're really just combinations of our other ones. I just like to go through and give some examples of quantities. Remember that terminology, quantities, which are measurable properties, and then the associated units for them. Right? And let's just do a couple more things that people might want to measure. Energy is one, and we'll just say, okay, well, I don't know what the unit on energy is, but maybe you do. But if you can come up with an equation for energy, like we said earlier for kinetic energy, in a previous video, kinetic energy is 1/2 mv squared. So, for example, and we know what m is. M is mass. And we know what v is. V is velocity. So your mass is going to be in kilograms. The 1/2 is unitless. Your velocity is going to be in meters per second, but that velocity term is squared. So we have kilograms, meters squared per second squared, kilograms, meters squared per second squared, which, for those of you who have looked ahead, know is a joule, capital J. All right? So a joule is a kilogram meter squared per second squared. And the last one that I wanted to glance at here is pressure. If you've ever put air in a tire on a car or a bicycle, you might have read those pressures in PSI, pounds per square inch. Well, that's actually pounds force, and then square inches would be a unit of area. So pressure, by definition, is force per unit area, right? And I just mentioned this isn't the SI unit, but you can have pounds force per inches squared, which is PSI. All right, that's not our unit we're working with right here. In fact, I'll cover it up with conveniently this brick that I have. So what is a unit for force, though? Well, we just established that force could be measured in newtons, and area could be measured in meters squared, right? So if you really want to step on that, you actually get a newton as a kilogram meter per second squared, and all of that is over meters squared. So the denominator there, denominator of the denominator is the denominator, and we can simplify that a little bit, and that meter cancels out one of those, and you end up with a kilogram per meter second squared, which is what we call a Pascal. So that is the SI unit for pressure, the Pascal. And that is how the derived units work, and we're going to get some mileage out of them working backwards. And let me just, energy is joules, pressure is pascals. And area would have been, had I been more careful, meters times meters, which is meters squared. And the reason I want to write that is because the SI unit for length would be meters, and the SI unit for width would be meters. And so the SI unit for area would be meters squared. You can see how I should have been yellow, yellow. All right, looks great.